Hello everyone, my name is Innocent Abel Krigiti, a Master of Science in Chemistry student at Ilanga University. I want to discuss about an article from Nature Communications entitled Rapid Self-Heating Synthesis of Iron-Based Nanomaterial Catalysts for Advanced Oxidation. So the main objective of this article is to produce a material which can be applied in advanced oxidation process. At the first place, what is AOP, or Advanced Oxidation Process, as applied in water treatment? Advanced oxidation process involves producing highly reactive oxygen species such as hydroxyls, radicals, as well as peroxide sulfate. These these reactive oxygen species can be applied in the process of degrading organic contaminants such as CAP or chloramphenicol. In order to produce this reactive species, we need some form of catalyst, and iron-based materials have been found to be one of the best catalysts in this process. So we can have different forms of iron, like zero-valent iron, iron oxide, supported iron catalysts, as well as ferrous sulfur compounds. And there are many ways to produce this catalyst. Among the ways is light source intensity, ultrasound assisted method, and using external energy fields. The most common way is to use external energy field, and the process is called pyrolysis. As we know, pyrolysis requires a large amount of energy in order to complete the process, and also takes time heating this material. That's why in this article they developed an iron-based nanomaterial catalyst via soft carbon assisted flash Joule heating. So a new technique here is flash Joule heating in preparing this material. We will dive deep into future slides. Okay, let's look at the FGH treatment process. The main process contains one reaction chamber. This reaction chamber we take our sample, then we introduce our sample between two electrodes. Once an electric current is allowed to pass through the sample gains a lot of energy and the electrons move randomly. While they are moving randomly, it means that at this point, since we use a very high amount of voltage or current, it means at the end we can obtain some form of flash. That's why this technique is called flash Joule heating. The process is so good that at the end we need to supply a high amount of current, which will generate a large amount of heat. This heat will help facilitate the process of converting our iron into an iron catalyst. So depending on the materials that you have, the raw material, we can make, for example, iron in combination with carbon. So we can have iron embedded on carbon as a support. This process is so good because it takes a very short amount of time, less than 10 seconds. You have already prepared your material, so that's why it's so interesting. Let me refer a little bit to the conventional pyrolysis treatment. As we know, in conventional pyrolysis, we need to take our material, put it in a chamber, then heat it with high, up to thousands of degrees, sometimes to thousands, but around 907 something degree for this case. Let's say, for example, for about 90 minutes. This is a lot of time, and sometimes we need to heat these materials for hours. So we consume a large amount of energy, and still the catalyst prepared is not very good. We will discuss this more. Okay, let's look face to face between these two techniques. As you can see here, we have two paths. The first path is the FGH path, and the other path is the pyrolysis path. FGH features include ultra high temperature, electrical field, and ultra fast cooling. It can greatly change the sample components and the structure. However, in conventional pyrolysis, the low temperature can barely change the structure, and the long-lasting duration lead to metal agglomeration. As you can see from the diagrams here, when we use pyrolysis, normally at the end, this, for example, these are raw material which contain carbon and iron, but at the end we almost have the same thing, because iron doesn't change and there's no any interesting new structures, as well as you can see the shape of this material is almost the same. So this material will not be able to support conversion of this species into reactive oxygen species. But on the other hand, when we use FGH, which is current induced heat, so as we supply heat to this system, it generates heat which self-heats. So this heat will again help in production of more and more activated material. Now, as we can see, it's interesting to notice that we have some form of heterostructures. Heterostructures in this material is a combination, like a nanocomposite, which contains the iron itself in a zero-valent form, as well as the iron sulfide, which is the raw material, embedded on our support. For this case, we have graphene. So if we look close, we can see that we have changed the structure of this material as compared to this, which can favor the conversion and production of reactive oxygen species. Looking further into the diagrams here, we can see that normally this process takes just a few minutes. At this case, it took around 3.5 to 15 seconds to be stable. And also, as we can see from the first picture here, we have smoke forming during time t is equal to around 1, but at the end of the reaction, we see that we have a lot of heat, a lot of amount of energy generated within a very short time of around 10 seconds. Okay, let's look about the component and the structure analysis of the iron-based material produced. From the imaging of transmission electron microscopy, it can be observed that the main composition is carbon, sulfur, as well as iron. Also, it's interesting to see that there is a heterostructure. Heterostructure, basically a composite containing iron sulfide, which is the raw source of iron, as well as a zero-valent form of iron, which is so reactive. It can also be seen that the percentage composition of these particles is on average around 16.8 nanometers. Also, we can further see from different analysis tools like the HADF STEM that we have carbon, sulfur, and iron in this material. Let's look deeper into analysis by XRD technique and XPS. The main thing to notice here is that we have this special form of zero-valent iron, which is the main target. As we can see, these are different materials that are prepared. This is the iron and carbon raw before treatment. This is treatment with pyrolysis, and this is treatment with FGH technique. It can be seen that only through treatment of FGH technique we obtain this zero-valent iron. Also, from the burning energy analysis on the XPS, it can also be noted that this zero-valent iron is also observed from the material produced by FGH treatment. Why is this a big deal? It's a big deal because zero-valent iron is a strong reducing agent compared to other forms of iron. So it can be very helpful in the reduction process to produce our reactive species, which can help in degrading the organic contaminants in water. Also, the analysis of the removal efficiency shows that this material outperforms the iron material produced, the iron catalyst produced by pyrolysis, as well as the raw iron carbon mixture. Let's discuss further about the catalytic mechanism for the PDS activation. PDS is one of the materials called peroxy disulfide, which can produce reactive species, reactive oxygen species. Now, as we said that we need to decompose this material, we need to break it down in order to produce this reactive oxygen species. It can be seen that once the attempt is tried to be performed by this newly heterostructure, which contains iron 0, as well as our iron sulfide material, this heterostructure is so important as it lowers the total energy of the transformation of this material. Then it means we break down this material and produce our reactive species. This is also one of the pathways that are involved in the decomposition of the organic contaminants cap. The main point here is once we have our reactive oxidation species, we can degrade this material into different chunks. Once we degrade this material, it means it will not behave as the original cap, which doesn't have much effect as compared to the original contaminants. Lastly but not least, the analysis and adaptability of the large-scale production potentiality of the FGH technology was also analyzed. From the analysis, it's interesting to see that the main factor that they have achieved in the novelty is lowering the energy consumption of the process. For example, we can see that from this figure, we have increased the energy consumption 34 times compared to using conventional pyrolysis techniques. And also, it's interesting to see that this work, although it generates high temperature, but it takes a very short amount of time to produce our material. So that's also an advantage. Since we have short time, it means we consume less amount of energy. But more interestingly too, is that this material can operate in different pH as a catalyst and at different soil samples, as also depending on the source of iron, it can still almost operate with the same efficiency. By conclusion, FGH technique prepared an electron-rich heterostructure which is embedded in graphene by synchronously ultra-high temperature and electric shock. The energy consumption is 34 times lower than the conventional pyrolysis, which is so important in large-scale production. Therefore, FGH can be used to synthesize iron-based materials and has a great promise in industrialization for large-scale AOP applications. That's all for my presentation, and thank you very much for listening.